Intro to hypothesis testing. So, we are going to look at a lot of examples that are similar to examples that we did with confidence intervals. Hypothesis testing gives us some of the same information that a confidence interval gives us, but not all of the same information. It is different in some ways. So we're going to learn how to do a hypothesis test, and we are going to compare the outcomes of a hypothesis test to the outcomes of a confidence interval. And hypothesis testing is the big thing in AP Stats. This is the thing that we have been building up to this entire year. After this, we've got a couple of small topics before the end of the year, but this is the big thing. So, really important. This first video is probably going to be kind of long. Sorry about that. But the rest of the videos in the section will be shorter. So, we talk a lot about gender discrimination because it makes for a very easy and simple scenario where we can conduct a hypothesis test. So in this case, we have 24 men and 24 women, and 21 of the men and 14 of the women were promoted. And we're going to find out if this is gender discrimination. So 88% of the men were promoted, and 58% of the women were promoted. So, what are some possible explanations for this? It could be that the promotion and gender are independent, there is no gender discrimination, we just happened to get a sample of women who were not very good at their jobs or whatever and did not get promoted. So, this would be our null hypothesis. The null hypothesis is that nothing is going on. Our results are just due to random chance. Another possible explanation is that promotion and gender are dependent, that there is gender discrimination, and the observed difference in the proportions is not due to chance. So this would be our alternative hypothesis. The alternative hypothesis is that there is something going on. And we have to demonstrate that with evidence. So one thing that we can do is we can do a simulation. So suppose that the null hypothesis is true. There is nothing going on. There's no difference in men and women being promoted. If we take a bunch of samples, sometimes we're going to get some results where there's a very large gap in the promotion rates. Most of the time, we're going to get that there is not a very large gap. We're going to get samples that are pretty close. And if you notice that this looks approximately like a normal curve, that is not a coincidence. Right? The promotion difference that we got was that p hat male minus p hat female was 0.3. So what is the probability of getting a difference of 0.3 or higher? Not very much, right? Based on our simulation is if there is no difference in the promotion rates, it would be very unlikely for us to get a difference of 0.3 or higher. So we say, since it would be very unlikely for us to get this difference, we would reject the null hypothesis. We say it would be very unlikely for us to see these results if there is no difference. So we do think that there is a difference. We think that something is going on. So we reject the null hypothesis in favor of the alternative. So the basic concept of hypothesis testing, we start with a null hypothesis, H0, that represents the status quo. We also have an alternative hypothesis that represents our research question, which is, what are we testing for? We conduct a hypothesis test under the assumption that the null hypothesis is true, either via simulation or traditional methods based on the central limit theorem. We're mostly going to go with this. Simulation is time consuming. The central limit theorem is just some math we can do. If the test results suggest that the data do not provide convincing evidence for the alternative, we stick with the null hypothesis, right? The null is our default. It's our assumption. If we don't have enough evidence in favor of the alternative, then we stick with the default. We stick with the status quo. If they do, then we reject the null in favor of the alternative. We always reject or don't reject the null. We never accept the null. We never accept or reject the alternative. We reject or we don't reject the null. Those are our two options. So just like with confidence intervals, we can do hypothesis testing on proportions or means or differences of proportions or means or paired data. This one, we're going to start with an example using a population mean, but we'll talk about examples for each of the different types of hypothesis testing in subsequent videos. So in a previous example, at some point in another video, we calculated a 95% confidence interval for the average number of exclusive relationships college students have been in to be 2.7 to 3.7. Based on this confidence interval, do these data support the hypothesis that college students on average have been in more than 3 exclusive relationships? So our hypotheses, right, our null hypothesis is that college students have been in 3 exclusive relationships on average. So the average number of relationships students have been in, mu, is equal to 3. Your null hypothesis is always going to be mu or p is equal to something. The alternative hypothesis is that college students have been in more than 3 exclusive relationships on average. So mu is greater than 3. Your alternative is can be mu or p is greater than something, is less than something, or is not equal to something. And which one of those you choose depends on what your question is. This question says specifically more than 3 exclusive relationships, so we can, we would know that this would be a greater than. The question usually is going to indicate which direction you're looking for. It'll say more than or less than or different from, not equal to. In our confidence interval, right, if we were just looking at this confidence interval, if I said, do we have convincing evidence that college students on average have been in more than 3 exclusive relationships, hopefully everyone would say no, because 3 is in the confidence interval. It could be more than 3, but 2.7 and 2.8 and 2.9 are also in the interval and therefore are also plausible values. So we have plausible values that are less than 3. We could not say that students have been in more than 3 exclusive relationships on average. The hypothesis test equivalent of that is, since the null value is included in the interval, we do not reject the null hypothesis, right? So the equivalent of it's in the interval, we don't have evidence, is we do not reject the null. This is the quick and dirty approach for hypothesis testing. It doesn't tell us the likelihood of certain outcomes under the null hypothesis, right? How unlikely or how likely is it for us to get an interval like this if the average really is 3? So the hypothesis testing allows us to be more specific in some ways. Hypothesis testing gives us a p-value, which is the probability that we get the results that we get if the null is true. And we use that to make a decision. Another survey asked how many colleges students applied to. 206 students responded. Got an average of 9.7 college applications with a standard deviation of 7. College Board website states that counselors recommend students apply to roughly 8 colleges. Do these data provide convincing evidence that the average number of colleges all Duke students apply to is higher than recommended? Right? So, which of the following is not a condition that needs to be met to proceed with this hypothesis test? It's D, right? This is a condition for proportions. Some of y'all struggled with these questions on the last test, multiple choice type questions, right? That's a condition. That's the large count condition for proportions. This is for a mean, right? The average number of colleges. So this is for a mean. D is for a proportion. D is the one that does not need to be met. But students in the sample should be independent. The sample should be done randomly. Sample size should be less than 10% of all Duke students, and the distribution in the number of colleges students applied to should not be extremely skewed. We then use this test statistic to calculate the p-value, which is the probability of observing data at least as favorable to the alternative hypothesis as our current data set if the null hypothesis were true. If the p-value is low, lower than the significance level, alpha, which is usually 5%, we say that it is very unlikely to observe the data if the null hypothesis were true, and hence we reject the null. So alpha level is our somewhat arbitrarily decided cutoff for how low is low enough, right? It would not be good research design to do the experiment or do the observational study and then look at the p-value and say, 0.07 is pretty low, I guess, right? We need to, ahead of time, before we do the research, decide how low would be low enough for our cutoff. And that's our alpha level. Which is not to say that people don't do that. It is, I guarantee you that people do their research with an alpha of 0.05, and then they get a p-value of 0.07, and like, oh, well, it's statistically significant at the alpha equals 0.1 level. But that's cheating. Don't do that. Bad research design. But our typical alpha is usually 0.05, 5%. That is just considered a good rule of thumb for the same reason that our confidence interval is usually a 95% confidence interval. It's a good balance between precision and accuracy, basically. So we usually go with 5%. In general, when I give you homework problems and stuff, I will try to remember to specify an alpha level. And on the AP test, they should specify an alpha level. If there is no alpha specified, use alpha equals 0.05, because that is by far the most common. Some research, for instance, medical research, is going to use a lower alpha because the consequences of making, I think that would be a type 1 error. We'll talk about the type 1 and type 2 errors later on. But the consequences of being wrong are much more serious if you're doing a medical study for a new type of drug versus if you're, finding the average number of relationships a college student has been in. That does not have nearly as serious consequences. And so the alpha level does not need to be as high for that one, or does not need to be as low for that one. So if our p-value is lower than our alpha, we reject the null. If the p-value is higher than our alpha, we say that it is likely to observe the data, even if the null hypothesis were true, and we do not reject the null. These are our only two options. We reject or we do not reject the null. Always, always, always. You never accept anything. You never have anything to do with the alternative. Your conclusion should always be to reject or not reject the null. So, a visual representation, right? So if so our null is that the average number of college applications that Duke students apply to is 8, the recommended number. So if the true population mean is 8, and we met all of our conditions, one of which is the normality condition, so we can assume that the sampling distribution is approximately normal, and we had a standard deviation of, 7? I go back. Yeah. Standard deviation of 7 and an n of 206. So, S was 7 and n was 206. So the mean of the standard deviation of our sampling distribution should be S over the square root of n. Technically, it'd be sigma over the square root of n, but we approximate that using S, right? So 7 over the square root of 206. And we should get a sampling distribution that looks approximately like this, okay? So where is 9.7 on this distribution? Turns out it's way over here. And so this gets us a z-score. If you find the z-score value for 9.7 with a mean of 8 and a standard deviation of whatever that is, it's a z-score of about 3.4. So we can use the normal CDF function on our calculator to find out what is the probability of a z-score of 3.4 or greater. And you can probably tell from this this graph that it's pretty tiny. It is a p-value of 0.0003. So, if the average number of colleges applied to by Duke students actually is 8, the probability that we would get a sample of 206 students with a mean of 9.7 or greater is 0.0003. That is a very small p-value. That is less than an alpha of 0.05. Right? That's a very small chance that we could just randomly get a sample with these results if the average number of colleges is actually 8. So, our conclusion is that the average number of colleges probably is not 8 for Duke students. Average number of colleges applied to. Probably not 8, because it's very unlikely that we'd get these results if it was 8. So we say it's probably not 8. It is probably closer to 9.7 than to 8. So we reject the null hypothesis in favor of the alternative hypothesis that the average is closer to 9.7. Right? So when we're examining a proportion, we find and interpret the p-value according to the nature of the alternative hypothesis. So, right, your null hypothesis, so for a proportion, it's the same for a mean. It doesn't really, it's not specific to a proportion. It's the same for a mean. But let's use the example of the proportion because we're doing this here, right? Your null hypothesis is that p is equal to some value, which is called the null value, right? So a lot of times for a proportion, this is 0.5 if we're trying to find whether a majority do something. So a lot of times our null value is 0.5. Not always, but a lot of times. So if your alternative hypothesis is that the true proportion is greater than that, you're going to be looking at the upper tail. If your alternative hypothesis is that the true proportion is less than your null value, you'd be looking at the lower tail. And if your alternative hypothesis is that the true proportion is different, but you don't care which direction, that's a two-tailed test. And so what you can do is if your z-score is positive, you do the positive part. If your z-score is negative, you do the negative part, and then you multiply it by 2. So you should get so this is why it's important. One of the things in our procedure for a hypothesis test is to draw a picture, and this is why. So going back here, right, we got an x bar value that is greater than our null value, right? This is the null value. Our null hypothesis was that mu equals 8, right? So that would be the null value. Since we got an x bar that's greater than that, and therefore we got a positive z-score, we would be looking for the area in the upper tail. If the question was, do we have evidence that the mean number of colleges Duke students apply to is different from 8 instead of specifically greater than 8, then we would also be looking for this much in the lower tail as well, which, because your normal distribution is symmetric, you would just take this and multiply by 2. Okay, so we get a p-value of 0.0003. If the true average of the number of colleges Duke students apply to is 8, there is only a 0.03% chance of observing a random sample of 206 Duke students who on average apply to 9.7 or more schools. That's a pretty low probability. For us to think that a sample mean of 9.7 or more is likely to happen simply by chance. So since our p-value is low, lower than our alpha of 5%, we reject the null. The data do provide convincing evidence that Duke students apply to more than 8 schools on average. The difference between the null value of 8 schools and the observed sample mean of 9.7 schools is not due to chance or sampling variability. So, here's how to get full credit for a hypothesis test on the AP test. The 4 steps are very similar to our confidence interval. We have slightly different things in each of the 4 steps, but it's still the state, plan, do, conclude. So, state the parameter you want to estimate, the actual statistic that you got, the hypotheses, and the significance level. So for the colleges example, the parameter that we want to estimate is the average number of colleges that all Duke students applied to. The statistic was an X bar of 9.7. Our null hypothesis was that mu equals 8. Our alternative hypothesis was that mu was greater than 8. And the significance level alpha was 0.05. Plan. Identify the procedure and check the conditions. These are, this is the same as with the confidence interval. For this one, this was the one that we just did with the colleges is a one sample, technically should be t test for me. I think we used a z-score, but that's because our n was high enough that the z and the t would have been basically the same. But for a mean, technically we should do a t-test. So, different from a confidence interval. For a confidence interval, we said interval. Now it's a test. One sample t-test. This part and this part are the same. One sample versus two sample, t versus z. All the same according to the way we did confidence intervals. The difference is that now it's a test instead of an interval. Our conditions, random, 10%, and the large counts. For a proportion, it's n times p0 is at least 10, and n1 minus p0 is at least 10. For a mean, it's going to be the same normality condition. Either the population is normal, or your n is at least 30, or there's no strong skew and outliers in the data. Just the same as with confidence interval. Your do step, your general formula is that your standardized test statistic is equal to the point estimate minus the null value divided by the standard error. Specific formula for a proportion is going to be this. For a mean, it's going to be x bar minus mu 0 over sx over the square root of n, where this is your standard error for a proportion or a mean, and then this is your statistic minus your null value. Your statistic being either p hat or x bar, and then your null value being either p0 or mu 0, right? Null value being whatever you used in the null hypothesis. Your do step should include a picture of a normal curve. So always sketch the curve, right? So 8 and our value of 9.7 and shaded in. It doesn't have to be a great sketch. Nobody is judging you based on your drawing ability. What you do need to do is make sure that you've shaded in the correct direction. That is a thing that they look for on the AP test, and there are a couple of ways to fulfill that condition, but sketching it is probably the easiest. So, get in the habit of always drawing the picture of your curve. Include the test statistic. The test statistic is the t or the z value. So whatever you get as an answer for t or z once you do all of this work. And then do the p-value. You're going to do the p-value on your calculator, but you should write down what you do on your calculator. So if you do normal CDF or TCDF with, lower bound, upper bound, lower bound of, say, whatever, 2.5 something, upper bound of 1E99, 0, 1. right? You should write that and make sure you label these. I'm not going to bother right now, but if you're doing anything where you have to write down what you put into the calculator, make sure you label them. And that should give you a p-value of something. So, your do step should show all of your work and include a picture of the normal curve, the test statistic, which is the t or the z, and the p-value that you get. And then your conclusion, assuming that the null is true, there is a p-value probability of getting p hat or x bar equal to your sample statistic purely by chance. Because your p-value is either less than or greater than alpha, we either reject or don't reject the null, and we either have or do not have convincing evidence that whatever the context is. You will learn to be able to say this in your sleep. A poll by the National Sleep Foundation found that college students average about 7 hours of sleep per night. A sample of 169 college students taking an introductory statistics class yielded an average of 6.88 hours, with a standard deviation of 0.94 hours. Assuming this is a random sample representative of all college students, which is questionable, but we'll make that assumption. A hypothesis test was conducted to evaluate if college students on average slept less than 7 hours per night. Right, so just to sketch that curve, right, our null value is going to be 7. Our null is that the average is 7. Our alternative is that the average is less than 7. We got 6.88. So our p-value is going to be this area. And this p-value is 0.0485. Doesn't give us an alpha level here, I don't think, but we'll assume that the alpha is 0.05 because that is by far the most common. So, if our alpha is 0.05 and our p-value is 0.0485, then the p-value is less than alpha. And if the p-value is less than alpha, we reject the null. So, reject the null. The data provide convincing evidence that college students sleep less than 7 hours on average. What's the problem with C? The data do not prove anything, ever. The data provide evidence, but they don't prove anything. Problem with E. E is making a conclusion about the sample. We don't need convincing evidence. We don't need to do a hypothesis test for evidence that students in this sample sleep less than 7 hours on average. We know students in the sample sleep less than 7 hours on average because we got the sample mean. We are doing inference on the entire population. So your conclusion should be about the population, not about the sample. If the research question was, do the data provide convincing evidence the average amount of sleep college students get per night is different than the national average, then the alternative hypothesis, instead of being less than 7, would be not equal to 7. And so we got 6.88. We would get the amount in that tail, but we would also get the amount above that, the same distance away from the mean in the other direction. And so in order to do that, you multiply your p-value by 2. And so in this case, we would get a p-value greater than alpha, and we would not reject the null. Hypothesis tests are not flawless, right? So to use our court system analogy, innocent people are sometimes wrongly convicted, and guilty people sometimes walk free. Similarly, we can make a wrong decision in statistical hypotheses tests as well. The difference is that we have the tools necessary to quantify how often we make errors in stats. So, We have two competing hypotheses, the null and the alternative. In a hypothesis test, we make a decision about what might be true, but our choice may be incorrect. So, there are two possibilities, that the null is true or the alternative is true. And we have two choices. We can either reject the null or fail to reject the null. If the null is true and we don't reject it, that is a correct decision. Good job. Go us. If the alternative is true and we reject the null, that is also a correct decision. The problem would be, one problem would be if the null is true and we reject it. That is called a type 1 error. A type 1 error is rejecting the null hypothesis when the null is actually true. A type 2 error is when we fail to reject the null when the null is false and the alternative is true. I do not have a good way to remember the difference between a type 1 error and a type 2 error. I've been trying to find a good mnemonic and I have not been able to. So if you think of a good way to remember these two things, let me know, because that can be tricky. We almost never know if the null or the alternative actually is true, but we need to consider all possibilities, including the possibility that we might be wrong. So, if we think of the hypothesis test as a trial, then the null hypothesis would be that the defendant is innocent, and the alternative is that the defendant is guilty, right? That's the thing that we need to provide evidence for. So, if we declare the defendant innocent when they are actually guilty, that's a type 2 error, right? We failed to reject the null when the alternative was in fact true. Declaring the defendant guilty when they're actually innocent would be a type 1 error. Which error do you think is the worst error to make? Generally, we think that the type 1 error is worse. Declaring a defendant guilty when they're actually innocent is generally considered worse than letting a guilty person go free. And this is somewhat reflected also in our the way that we've set up our hypothesis tests. It is worse to make a type 1 error saying that we have evidence of something that we don't have, rather than making a type 2 error, which is saying we don't have enough evidence, even if the alternative might actually be true. As a general rule, we reject the null when the p-value is less than alpha, the significance level. So, for the cases when the null is actually true, we do not want to incorrectly reject it more than 5% of the time for an alpha of 0.05. So, a 5% significance level means that there's a 5% chance of making a type 1 error if the null hypothesis is true. So, probability of making a type 1 error, given that the null is true, is alpha. So, that's why we prefer small alpha values. Increasing alpha increases the type 1 error rate. And we generally think that making a type 1 error is worse than making a type 2 error. I mean, neither of them are great, but this is usually considered to be the worst one. So, traditional level for significance is 0.05, but we can adjust that based on the application. So, if making a type 1 error is dangerous or especially costly, we should choose a smaller significance level. We would want to be very cautious about rejecting the null hypothesis and demand very strong evidence favoring the alternative before we reject the null. So again, this is the medical studies right? A new type of cancer drug. It could be very dangerous if we say that this cancer drug cures cancer and it doesn't. So we need very strong evidence that this drug actually works before we can reject the null. If a type 2 error is relatively more dangerous or more costly, then we would choose a higher significance level. We want to be cautious about failing to reject the null when the null is actually false. There aren't a lot of scenarios where the type 2 error is more dangerous or more costly. It's usually just the case where a type 1 error isn't that bad, so we go with a higher significance level because it makes our results look better. The power of a test is the probability that we will correctly reject the null if the null is false. So it is the 1 minus the power is the probability of making a type 2 error. Or the power is 1 minus the probability of making a type 2 error. So, assuming your null is true, find the values of your statistic that would cause you to reject the null. So, for a two-tailed test, because I know the two-tailed test off the top of my head, right? So, a two-tailed test is equivalent to a confidence interval. So an alpha of 0.05 is going to have a z-score of plus or minus 1.96. So what you could do is use your z-score of, for instance, 1.96 to be your x-bar or p-hat minus your null value over your standard error, and you know what all of these things are, so solve for an x-bar, or you do the same thing for a p-hat. Now, assume that instead of the null value being the population parameter, your statistic is actually the population parameter, right? Find the probability of getting a value equal to or more extreme than the values that you calculated. So, you might get 1.96 here and negative 1.96, whatever values correspond to these z-scores here. And that would be the power of your test. And 1 minus the power of your test is the probability of making a type 2 error. So, your framework, you set the hypotheses. For a single proportion, it's going to be p equals the null value, and then p is less than or greater than or does not equal the null value. For a mean, it's going to be mu instead of p. Check your assumptions and conditions, calculate a test statistic and a p-value, make a decision, and interpret in context. If p-value is less than alpha, reject the null. There is sufficient evidence for the alternative. If p is greater than alpha, we do not reject the null. There is not sufficient evidence for the alternative. And real quick, a lot of our things are similar for confidence intervals and hypothesis tests. One big thing, and I'll mention this again in the next video where we do a hypothesis test for a proportion, but we're going to use for the standard, calculating the standard error, we use p-hat in a confidence interval because we don't have any other p-value. The only p-value that we have is p-hat, right? So we use that in checking our conditions and in calculating the standard error. In a hypothesis test, we do have another one. It's the null p-value, right? The p-value that we're comparing to in our null hypothesis. And since our hypothesis test assumes that the null is true, you want to use the null value as the p in your conditions and your standard error. That's it for right now. We'll come back to that in the next video.